Alright, in this video we're going to talk about discontinuities, or continuity, which is the opposite of that. Let me give you 3 examples where we find discontinuities. One example is if we have a line, or any graph, and a graph with a hole in it, like that, that is called a discontinuity, and it's a hole style discontinuity. A discontinuity basically means you have to pick up your pen, if you think about it when you graph it. Another example of a discontinuity, a common one, is a vertical asymptote. So say you have a graph that goes like that, and then maybe it goes like that. That vertical asymptote is a discontinuity because you have to basically pick up your pen and then start over again. Alright? And the last most common we're going to talk about is this kind, where you have a break. And these are usually come from piecewise functions. But it's usually where you have a break, where so you have to like this, and you have to jump down here and continue it. So you had to pick up your pen to do that. Those are the 3 most common discontinuities, or places where your graph is not continuous. Now, we're going to do it with equations, find discontinuities, and not graph them, but you will see that these, all 3, will come up within these equations. Alright, so let's talk about discontinuities here. Where would you find discontinuities? Well, when you have a fraction, the most common discontinuity is when you get a 0 in the denominator. You are not allowed to put a 0 in the denominator. So without even graphing, I could look at this and just look here at the denominator and go, what would cause the denominator x squared minus 25 to equal 0? What would make the denominator equal 0, causing an error in the function, which would then create one of these types of discontinuities on the graph? So let's solve that, and that will give us our discontinuities. So when you solve this, you're going to add the 25 over. When I add the 25 over, I now have x squared equals 25. Now how do you get rid of a square? You square root both sides. So when I square root both sides, I now have x equals the square root of 25, which is 5. But remember, it's plus or minus. A lot of people forget the plus or minus when you square root both sides. Because what squared gives you 25? A positive 5 and a negative 5, both, when squared, gives you 25. So I solve the denominator after I set equal to 0. And these 2 values, if I plug it into this function, will give me a 0 in the denominator, causing a discontinuity. Now the question we're going to talk about is which one of these is it? Now the question here doesn't even ask for what type, but I want to go there because it's important sometimes to know what type of discontinuity it is. So there they are. Let's talk about the type. And here's how you tell what type it is. First of all, what you do is you take these 2 answers and you plug it into the function. So I'm simply going to go, okay, what is f of, let's start with negative 5. All right, when I plug negative 5 into this function, I get negative 5 squared plus 5 times negative 5 over negative 5 squared minus 25. Again, I plugged negative 5 in for all the x's. And hopefully you'll notice here that becomes 25 and negative 25. So 25 plus negative 25, that would be 0. All right. And this becomes 25 minus 25, which is also 0. All right. So I got the answer 0 over 0, which is called indeterminate form. Now what does that mean? Well, what kind of discontinuity would this show up to be? Well, you would find out whenever you get a 0 over 0 as a result, when you plug in the answers you found for discontinuity with a fraction, you will get a hole. It would be this kind of discontinuity. So at x equals negative 5, we are going to have a hole. Okay, now let's plug in 5. We do the same thing, but we're going to plug in 5 this time. All right, so 5 squared plus 5 times 5 over 5 squared minus 25. And let's see, what do we get here? That would be 25 plus 25, which would be 50. And 25 minus 25, which is 0. Do you see how both of these got 0 in the denominator, like we talked about? But do you see how this one's 0 over 0, but this one's a number over 0? Whenever your answer is a number over 0, what's going to happen is your answer at x equals 5 whenever you have a number over 0, in this situation, it is a vertical asymptote. That's the kind of discontinuity. So it's this type. The first one is a hole. The second one is this. All right. Now, one more thing that can kind of be useful, you can know when it's a hole. One more way of looking at it is if you technically factor top and bottom. So if we factor the top, you pull a GCF of x out, you get x plus 5. If you factor this, you get x plus 5, x minus 5. And do you see how we can cancel here? Now, do you see then, if I were to set the bottom equal to 0, basically think of what would make this a 0. Do you see how it would be negative 5 plus 5? When I cancel that out, that means the negative 5 is a hole. Anytime you can cancel out a value, the opposite of this number is a hole. And what's left over is going to be your vertical asymptote. So the majority of the time, that's what's going to happen. You wouldn't even have to plug it in. And you can just, when you cancel, you will notice that the piece canceled will be the hole. And what's left is going to be the vertical asymptote, what's left in the bottom. Because what would create a 0 here? A positive 5. A negative 5 would have created a 0 here in these two, in this spot right here, but it gets canceled out, creating a hole. That's just a little shortcut. But it all depends if you want to do this canceling to find holes. This canceling type is called a removable discontinuity because you kind of remove it by canceling it out. It's whole. Okay, enough with that. Those are those two. So guess what type this one's going to be? Can you picture that? It's a piecewise graph. Now, what is a piecewise graph? A piecewise graph is a function g that is made up of two functions. Let me draw a little picture of this. Now, I wouldn't expect people to normally draw pictures to do this limit, but I'm doing it just so you can have a visual what's happening. If I graph this first function, 3x minus 2, that means I start at negative 2, and I go up 1, 2, 3 over 1, and I get this line. That right there would be this function. And then the bottom function is x squared plus 1. That one's going to start here, and it's x squared, so it's a parabola, a nice normal looking parabola. Okay, those are my two functions. Now, what is this over here telling me? Well, it's telling me that for g, we're going to use values less than 0 and use this graph. So if we look at this red line for values less than 0, not including 0, so what that means is I'm going to put an open circle there, and that right there, that green part of the red line is my graph, g. Do you see this function is greater than or equal to 0? That means I'm going to include this value and take the greater than or equal to 0. All right, so what happens is my function is now this line, open circle, and it continues with this half parabola. That is g. It's two graphs made into one. Now you could hopefully see this discontinuity. See how the break jumps up here and goes? So this discontinuity is the break type. But let's do it with a graph. How do we do it? So let's talk about how we do it when we can't or don't want to graph. So what you basically do is when you do find discontinuities, you basically just got to make sure these two graphs see if they meet at this value. So since this is 0, I want to see if these two are equal at 0. Okay, so I'm going to plug 0 into this function. So for g of 0, for the 3x minus 2, I'm going to plug in 0. That would be 3 times 0 is 0. 0 minus 2 is, yes, negative 2. And the other g of 0, the other side, would be what squared plus 1? Well, we plug in 0 again. 0 squared plus 1 is 1. What do you notice about these answers? They're different. Do you see how this function, negative 2, right there? Positive 1 is right there. Do you see how without graphing, we can tell that at 0, these two graphs are not going to meet? Now, if these two graphs, say, ended up being 1 and 1, these two graphs would have met, and it wouldn't be discontinuous at this point. But since they're different, it is discontinuous. So we know now that what we can say is at x equals 0, you have a discontinuity. All right, we can tell. We could also look at the graph, but if you didn't graph, you can tell since these values are not the same, where they're supposed to meet we know there's a discontinuity here. All right. Now, one thing you have to worry about on piecewise, and I don't have to on this one because this graph and this graph are both continuous. Now, how did I know that? Could you plug any number in for this function and create an error? No, it's a line. Could you plug any number into this parabola function and get an error? No. But what if, say, one of these had a square root? Well, I could say this was the square root of 3x minus 2. Well, we can't plug negatives into a square root. We can't take the square root of a negative. All right, so wouldn't that cause errors? Or let's say this one out here was x squared plus 1 over x plus 5. Well, you can't have a 0 in the denominator. So what if one of these two functions have a discontinuity by themselves? You have to watch out for that. Sometimes on piecewise graphs, each piece might have a discontinuity by itself. All right, it might look like this function down here, or this function could be the top one. And so you have to find each one's discontinuities and where they should meet. All right, now let's say you found a discontinuity on this one. But what if it's not on the interval where that graph is? Then you don't care about it. But if the discontinuity for this particular graph was on the interval, then you have to include it. So you've got to be really careful on piecewise. You have to check each individual one where they might have discontinuities and make sure if there is one, it's on the interval to count it as a discontinuity, because if it's not part of the graph, it's not discontinuous there. So be very careful. I didn't do that one on this example because I thought it'd be more things to confuse you. I wanted to kind of keep it simple. All right. So this piecewise, you always want to check where they should meet and if there's discontinuities on each individual graph. This one had one at 0. On fractions or rational equations or functions, you want to set the bottom equal to 0 and solve it. Then sometimes you want to know what type of discontinuity. And so you take your answers, plug it into the function. If you get a 0 over 0, it's a whole. If you get a number over 0, it's a vertical asymptote. You could also try to factor and cancel. Any cancellations will be a whole. What's left over will be vertical asymptotes most of the time. And again, these are the 3 most common discontinuities you run into. And the basic idea of discontinuity is picking up your pen. You have to pick up your pen. The way you see it when you're doing functions without graphs is values, discontinuities, are values that cause errors in the function. Those are the key ideas. Good job at discontinuities. It's a pretty important subject.